Thank you for having me here. This talk is about AOT and JIT in CLR. And as Brian said, today is all full of AOT and JIT talk. And I really enjoy Mark and Christian's talk. It's really nice. So this is today's agenda. I would like to introduce us to our problem space a little bit. I mean, it is AOT and JIT, but it's two different products, very similar product, but it may be for different audience. So that problem space I would like to introduce a little bit. And then I kind of want to walk you through the AOT journey that we have and how it plays with the JIT. So you can see from the agenda, I will talk about first generation of AOT, which many of you know as NGEN. And then we'll talk about second generation of AOT, that's CrossGen, which is going to be published in .NET Core 3.0. Then we'll talk about how AOT and JIT work together. And I would like to kind of broadcast a little bit about the future AOT that we are building and what we are building in that one. And we will end with a recap and the future. So this slide, after Mark's talk, it seems redundant. Runtime's universal challenge is always startup, steady state, throughput. He didn't cover size of distribution, but that is in actually one of our equation. And latency, people know. And latency, mostly well-known one is JIT latency and GC latency. And of course, there are other latencies that could happen, but it's kind of out of the runtime's control, right? Startup is a very interesting problem because, as Mark mentioned, like, what's the definition of startup? And if you ask everyone, they are going to give a different application type. You are going to get different answers. For example, UI application, that startup definition, maybe when it's the first form was almost finished drawing and somehow interactive, then you feel like it is kind of startup, right? And then how about services, like living in the cloud? It's almost like ready to serve a response and somehow provide a steady throughput to that request. That's how your definition of startup. I like Mark's diagram better than mine. So we should exchange a slide before we come here. And I thought this was quite artistic. It's my handwriting. We talk about, I kind of want to illustrate what startup is like. He also covered on his presentation. When processes start, runtime needs to initialize itself. And runtime start to load type JIT, prepare for user code to execute. And as user code execute, encounter new user code or the need new load type, the JIT and load type will happen again. So startup is actually where user code is actually not a dominating factor. It is runtime is doing the services to make sure that user code is ready for execution and hit a steady state. Mark also showed that how many classes need to be loaded in order to do the startup. And this is actually the kind of equivalent slide of Mark's. This is a Hello World web API. What it does is create a host, start a host, output a Hello World. And in our world, we need to JIT over 4,000 methods in order to start up. So as you can tell, the two words is actually very similar. Runtime initialization probably is kind of hard to eliminate, but that type loading and a JIT in order to get to a steady state is actually overwhelming in the runtime space. Before I go into the AOT and JIT, I kind of want to talk about the CLR design philosophies. Our design philosophy is, one, good performance out of the box. Excellent performance, maybe developer will need to intervene and we'll provide toolings. Second, we want to provide consistent first startup and second startup. Why is that important? Some of the workload may not have a chance of second startup. For example, phone applications. Once we are building phone application, in order to decide if an application is a good application or bad application, the fact it needs to reach the first form factor within a certain millisecond is actually a constraint on us. And if you do not pass that, you actually don't even pass the store validation. They believe that you are uploading some sort of bad applications. And also, long-running services, like a SQL Server, they never want to restart. So you never get a chance to do your second startup. Your second startup may be because something bad happened, that machine reboot. And so we want to be green, compile once, and reuse. We would like our performance characteristic, that steady performance characteristic, survive reboot. We also want our performance to survive servicing event. And that's kind of our mean bar. And we choose not to depend on interpreter, and that's by design. In our measurement, interpreter can close a certain gap of startup, but we believe with an AOT in our lab, in our measurement, an AOT done decent is going to be the interpreter. And interpreter also brings in another factor that is big in our world. It's actually diagnostic stories, debugging, postmortem, local inspection, setting a breakpoint. All those things are actually quite different from the JIT. In order to support that kind of behavior, we had to build two ecosystem of diagnostic. So waiting on that decision point, we choose not to depend on interpreter as our startup solutions. And the last bullet is actually, I wouldn't say at the beginning we come with a piece of AOT and JIT complements each other. I would say that in CLR world, at the beginning, AOT and JIT are actually trying to compete each other. AOT believed that startup is AOT's problem, not JIT's problem. JIT always believed that JIT can be so fast that we do not need AOT. But this slide, this bullet I put in there, because that's actually where we are today. With all our technology together, we actually believe AOT and JIT should be complementing each other so that we can get good startup and we can get good steady state. We have different design decision points for AOT tech. So before we picture out our AOT tech, we have a bunch of questions that we ask ourselves. First one is actually, where can the native images be generated? Device, cloud. There are a bunch of different places that you can see that being generated. Can you be generated in an arbitrary machine and being ported to a different machine, completely different architecture, different platform? And those are questions that you kind of have to answer yourself, right? And where does the generated code live? In a cache, embedded, you're going to see that we do both, or somehow in a different places, right? And what size is acceptable? This is actually also a very critical point to remember. Many workload does not care about size, but many different scenario cares about size. Thinking about phone, I know we are in America, we always enjoy the fast internet connections. Yes, thinking about going to a place that the wireless connection is much slower. The application that you download over the wire, how long does it take to install, right? That size over wire matters, actually translate to size on disk as well. And also, size doesn't matter. If you look at Alpine, the OS operating images that by itself is less than 5 megabytes. If an application come in and take 100 megabytes, does that even make sense to anybody? No, right? So it's not like everybody care about size, but there are places care about size. And we need to ask about, does it need to support servicing event? What kind of servicing event it is? And is it arbitrary or is it well-known? And how do we take advantage of that knowledge? Trust signing. This is also a big one. When you're trying to generate images, how do I know that images either is a cache in memory or it is on disk? How do I know it's not tempered? How can I trust it? And trust and security is actually a very important aspect of today's compute. Even in the cloud, you must trust the cloud, right? Then how do you know that thing that you upload is what you being executed, right? So that is also a very important factor in our design. So this is our first generation of AOT, and I may not check everything green in that first generation of AOT. This generation of AOT, many of you know as NGEN. So where can images be generated? We generated native images on the target machine. So for example, if a desktop, you download the I/O, and you actually have to generate the native image on that desktop. On a cloud server, after you download your application, if you want to generate native images, it's after the download, you have to trigger an NGEN command to get it generated. And this image itself is actually interesting. The format that we choose is similar to a PE file, and by the way, this is the first generation. That means we only live on a Windows. This is not applicable to Linux. We actually enable cross-process sharing, just like a DLL. Where does the generated code live? Actually, today, in the NGEN images today, even though this is the first generation technology, it still exists in the laptop and even in the cloud. If it depends on the full desktop, this is the AOT tech power it. All the other second generation, third generation, we never port back to the desktop. So we save each of DLL's native images into another separate DLL. And later on, I will have a diagram to show the relationship of them. And size, at that time, we think size acceptable is good enough because we did not have the challenge of the phone devices or the Alpine. Does it need to support servicing event? And the answer is yes, this technology must support servicing event. CLR4 framework is serviced through Windows Update, and there are class library being installed on the machine. Those class library could be updated too. Application can be updated. None of these update events are synchronized. So things can go change underneath you and not in your control. Trust and signing, well, that was the first generation, so we didn't really take care of the trust and signing. So we generate on the machine into a DLL, and then we just use it. What is being persisted by NGEN.exe? Remember that friendly diagram, not as fancy as marks? So let's go back to that diagram again. Runtime being initialized, we load type. When runtime loads type, it generates data structure. The data structure that we generated, we call it E data structure. And JIT codes from IO to native. Java's world is bytecode to native. And there's a native code. And some user code runs, right? And then you JIT again, and you generate more native code. You load type, you generate more E data structure. And the blue boxes are runtime artifacts to support running user code. And blue boxes are actually what we persisted out. This is a code example showing you the generic, how hard it is in the CLR world. This simple code example has a base class, has an interface, and has a generic type derived from called samples, derived from base, and implements iFace. And also has a value type. Yes, we have a simple struct over there. It's just a field of integer. And the main is just simple. I kind of simplified it and want to show you the places that is actually make us different from Java's world. The three yellow highlights are the instantiations. And those are not type erased. That means each of them at runtime will have their identity, type identities. And each of them will have their own copies of code that actually will execute. So far, so good? So this is what the data structure like in the CLR runtime. Method table is kind of one-to-one mapping is our type identifier. That is actually really uniquely distinguish one type from the other, even in the generic instantiation world. So in this particular case, you will see sample string, sample object, sample struct. Sample in I put in there, even though my code didn't show it, but it's very likely somewhere else in the code could use it, and that's yet another value type instantiation on a generic. E class is actually where that holds a collection of method descriptors. Method descriptor is, in our world, is how you hold the relationship between IO and native code. And that is how things being executed. Taming the size. Since generic instantiation is a runtime artifact, when you're trying to generate code ahead of time and you persist out all the possible generic instantiation into the images, that images actually will explode. And not to mention, CLR, just like Java, is actually a very rich dynamic reflections. We can make type at runtime by using a string. And there's no way that you can predict them ahead of time, right? So how do you predict what it matters to generate? And when you generate them, you generate too many, so you must figure out a way to tame the size. What we're trying to do is actually we're trying to aggressively fold similar data, like string interning and like, some of the hash compression. And then we also trying to figure out what else we can compress them together. In this particular case, we have some observation that's actually really interesting. That is, generic instantiation over different reference type are the same, because reference type is just a pointer size, right? And the code generated for them are the same, but code generated for generic instantiation over value types may not be the same, because the value type usually comes in different sizes, and even with that, even if the size is the same, if the different field that you passed in the instantiation, the layout could be different. And so, with that, what we did is we fold. This actually picture trying to show you how we fold the things. The orange boxes, master disk, is actually where the most expensive. Even in my diagram, I only show 2. You usually probably know a class will have many, many methods. It could be over 100, even you define many, but the base class hierarchy that you define port in, and interface stuff that you got in, right? So this diagram shows how we fold the data structures. Method table, we cannot fold because they are identifier. You fold 2 identifier to 1, that means you lost type information. However, the E class, we can fold. You can see the first yellow box. We introduce a type called _canon. It's actually trying to represent, like, this is actually symbols of T for all the reference type. And so with that, we actually fold the method descriptors and E class into 1, and then you also see a method table with a canon just because we had to satisfy that pointer relationship. This diagram may not striking that we save a lot of space, actually does. Because my example only give you 2 generic instantiation over reference type. In real-world execution, it's actually way more than that. Any questions? Okay. So now come to the next question. Where do these AOT images live? I draw some solid blue boxes to think about them as a jar file. In our world, it's actually DLL. Our DLL can contain more than 1 class. So if D have dependency from A and dependency from B, and A and B both have dependency from C, a very common case, it could be C contains object, assistant.object, your object type. You derive from them class library, A and B, and then D is your application. It's actually a very normal diagram. And when we have NGEN images for C is actually guaranteed because a framework does not have the NGEN images runs way too slow. And there's a B by being NGEN and D being NGEN. And we are actually really picky about using the images. Before we can, for example, you are running D, before you can use D.ni.dll, we actually will have to do some sort of closure walk to ensure that upon execution, it is actually B and C, exact version of B and C will be used. So we can use the D.ni.dll. So D.ni.dll actually remember when it's being generated, what versions of B, what versions of C are actually used to generate that. Now, it is servicing event happens. I choose the root C prime. Think about framework being updated, Windows update push down a framework update on you, then actually all the NGEN images are invalidated. So we need to get to a C prime.ni.dll, B need to be able to get to a shadowed B prime ni.dll, D need to go into a D prime ni.dll. And this is actually, so we carefully choose boundary logic. The generation of C prime ni.dll happens on Windows update because we actually say that if no NGEN image exists at all in our framework, it's actually not a supported configuration. So it's actually part of that update. Now, question is, where's the B prime and D prime going to be regenerated? We have an elevated service task to deal with servicing. And servicing is going to run code because you're going to trying to compile B and D.dll. So this elevated service task runs at 2 a.m. you will search your breadcrumb. Remember d.ni.dll, remember the version of the DL that it depends on when it got generated. You will do those validation. If you find that version actually is no longer there, or like a new update happens, then you will know that you need to regenerate it, right? So when it finds invalid NGEN images, it will try to regenerate it. At this time, you probably can tell NGEN itself, it's a story holds together, kind of, but it holds together in a thin while. Anything got invalidated may not work. For example, this service task actually is supposed to wake up at 2 a.m. and run it. What if you are working late at night and you do want this thing to be intruding yourself? Or what if you shut down your laptop when you go to bed? I may never have 2 a.m. to run it because you just shut it down, then when am I going to run it, right? And when the NIDL does not exist, application still runs. As long as the framework C is still NGEN, performance is somehow acceptable. Everything else will fall to JIT. Second generations of AOT. Why do we do a second generation of AOT? When we decided to go open source and go cross-platform, we no longer have certain privilege that we got from Windows. Some of the privilege that we got from Windows, including some of the GC that we have, like a write watch, that's a Windows API. Going to Linux, you don't have it. For NGEN specifically, we actually do not have an elevated task anymore. Think about it. You have an arbitrary Linux distro, and I go there and say, I want an elevated task. Who is going to trust me, right? So we need to go back to the whiteboard and re-examine our questions, like, where can an image be generated? Where does the generated code to live? And we need to support servicing event without elevated service task. And what should we do? So this time, when we look at the images must be generated, we concluded that maybe it can be generated on device, but we should really enable build-led generation so that it can generate once and deploy it in many places. This is extremely powerful in server's case. For example, Bing. In their build lab, they generate native images, and when they're trying to kick off the server with their daily night build, the images go out and does not need to rebuild on those server instances. And portable. Portable is a wild term. How portable is portable? It's not like a 0 and 1, right? Portable could be a narrow margin of portable that is actually, I say, when I generate the native images, it is actually in a, for example, similar hardware, similar operating system to be mismatched hardware, even in the business, or mismatched platform. In this second generation, what we choose is actually, we can move from one machine to the other, and those two, the operating system somehow had to be similar. For example, Windows or Linux. Different distro Linux may just work, right? And different versions of Windows will work. You don't need to match that. And this one, we were not quite able to do the business mismatch. And we were not able to do the platform mismatch either. And where does the generated code live? So in the first versions of AOT tag, we kind of do a shadow DLL, which is kind of annoying because you have extra file you need to copy. You have extra file you need to load. You get a benefit of the ahead of time, but loading extra file, loading extra DLL always slows things down. So this time, we actually choose to embed the pre-generated code into our IO DLL. And so the number of files did not get larger. Yes, it loses some sort of portability. In theory, you could have choose to fall back to the JIT if pre-generated optimized code does not match the architecture of platform that you actually deploy to. We have not built that. We could build that, yes. There's always things that we can build. We are just a software engineer, right? Yeah. Does it need to support servicing event? And at this time, when we build a second generation of the AOT, our answer is still yes. Because this is our .NET Core story. And when .NET Core started, we were told everything is out of band. Every DL could go out by itself. We don't have a control. Don't even forget about class library or application code. It's just framework itself. we are going to be agile as possible. So yes, we must support arbitrary servicing event. Trust and signing, yes. Since we build on a build lab, we can always sign it. And that should be fine. And size constraint, yes, had to be reasonable. You have an ILDL, you embed some pre-generated code into it. You will hope that your DLL size do not become 10 times larger, right? So all the taming that we talked about early on still applies. So how can the images live through servicing event and be portable? We kind of take a naive approach because we need to ship, right? So don't depend on anything outside of current module. That seems like a safe assumption. That means do not do early type layout because other than system.object itself, everybody depends on it. It's a cross-module dependency. And since that DLL can be serviced independently, I cannot trust any type layout. The second one is usually scale back all the code optimization, such as inlining from cross-module. We are also, because of that, we actually lose opportunity to devirtualize method. And I would say Java and C#.NET are actually very similar. We are object-oriented languages. And the power to devirtualize, enable inlining, and further doing optimization actually is a key part of performance, right? So if you go back to this our frame diagram, so the data structure, I X them out. What I'm really writing out now is just native code, and I embed to my ILDLs. And those native code got embedded in, it's not quite exactly the same as NGEN. This example give you a kind of a taste of how much of scale back that we do. So this is just in general just a simple function. And what we are trying to do is actually we receive an O, it's a gen-based class T. And we are just trying to invoke two string methods on that O. And if you look at the generated code on both sides, NGEN is on your left, and CrossGen is on your right. The highlighted one in green is actually where that matters. You will see the green highlights on the NGEN CodeGen. We actually do a vtable lookup and then get a vtable, and we know exactly that offset is 20 hex, and we directly call into it. And that's why it's being highlighted in green. Now, if you look at the CrossGen, you will see we are actually going through the virtual step dispatch. And because you need to have resolution at the runtime to ensure that your core target did not get moved, you can no longer hard-code it in offset. That's actually 5 more instructions before hitting the target. And that's assuming fast pass as well. So with that, I go back to measure my startup. Actually, it did not look too bad. So apparently, type loading is not where slow everybody down. It was actually legit, even though JIT denied it. So this kind of shows the differences. You can see 4.7.1 is actually our desktop version. So you see a JIT number, you see an NGEN number. CoreRT is the JIT number and CrossGen number. I would say they are close enough. You might wonder why CrossGen and CoreRT are a bit faster than NGEN, which is not true. Because remember, that all those things depends on the framework that it depends on. The desktop's framework is actually bigger than the CoreRT framework. So the fact that I quoted 4,000 need to be JITted in order to run WebApi, hello world, is actually CoreRT. If you go to the desktop, the number could be bigger. It's just because the framework codes stack on it are different. So it was close enough, but we just saw the scale back on the persistent native code. Is it really not noticeable? Remember the bunch of things that we talk about, runtime cares, startup, and throughput at steady state. So we went back to the build lab and then perf lab, and we remeasure our throughput. JSON serialization benchmark is actually quite well known. This is a response per second, so higher is better. You can see JIT and CrossGen has differences. JIT actually are able to serve more response than CrossGen. It's about 7% more than CrossGen. And this is where the unfortunate result when you suffer from the lesser code quality. So how do we fix it? So this is the time we turn to the JIT and say, can you help? Before I jump into how JIT come to help, I would like to share some of the CLR JIT history. Historically, CLR invests a lot more in the AOT tag than JIT, and I was told that you would not be impressed by our JIT story. So we started Windows only. We started with x86 only. We have a JIT. We call it JIT32. It is a tree-based JIT, and you know how to generate x86 code. When 64-bit comes, actually two 64-bit comes at the same time. Yes, IA64 as well, even though we think that it's not here, but we are still servicing on it, and x64. We went back to our JIT32 and look at that design. It was not designed with 64-bit in mind. So at that time, our decision is, do we re-architecture our current JIT or we seek help because we need to ship? Usually requirement come to you, you have a year or two, right? So actually at that time, we pick up a different JIT. It's actually our UTC backend, and we took it as a JIT because it knows how to generate x64 and IA64. And then when ARM32 comes, we went to the JIT32 and make it able to target ARM32. And then later on, we say, this is not scalable. If we are tuning uniting heuristic, we actually do two places. And remember, performance is a compatibility bar. How do you justify inlining heuristic tuning on one JIT and to the other JIT? Actually, result does not match. That was actually really, really difficult. And that is when we decided to unify the JIT. This is our unification story. We hope that we have one code base to work on, so we don't have to do work twice in totally different code bases. And today, if you go to CoreRT, you go to that JIT directory, it is ReuJIT that you are seeing. ReuJIT is actually tree plus SSA based and with linear IR. And this is the only code generator that we have knows how to generate Linux and also ARM64. So that kind of put it in there. We try really hard to bring ReuJIT to light earlier, but it was really difficult, not until .NET Core, because we talk about performance as a compatibility. When we're trying to bring ReuJIT to replace JIT32 on desktop, we are not quite able to because the code generated is somehow different, performance characteristic is somehow different. Some people see wins, and one person see loss, and that person is going to shout out loud. And that is pretty much all our developer ecosystem, right? The unhappy one always speak out. And so it was not until like about 2 years ago, we finally unified all of the effort on .NET Core with ReuJIT. And this ReuJIT gives us two modes. One is quick JIT, the other one is actually full optimized JIT. When JIT try to optimize, remember earlier on I mentioned that diagnostic is actually a big thing for us. So probably you also know that to get a good debugging story with optimized code is not trivial. It's not like undoable. It's not doable, but it is actually not easy. And you can get close. Will you get perfect? Maybe not. So we actually have two flavors of JIT, two modes of JIT. Quick JIT, actually trying to generate code as fast as possible, and turning off the optimization, so debuggability is actually easier. And the full optimization JIT actually generate better code, but you probably guess it probably runs a bit slower. And so the trade-off is always the same. If things can go really fast and generate perfect code, I think half of the people in this room probably will be losing that job security. So how does JIT come to help? For a long, long time, our CLR has one assumption, that is one IO method body only has one native code copy. And in order for JIT to come to help, we know that there are some AOT images code gen is not as good. We need to be able to generate another copy and try to use it. And so this is what we call tiered compilation. We were hoping that we can generate code multiple times for a single method, right? And then method body itself has some sort of versioning story. If you look at that diagram, you start with an IL. Some of the IL will have, in the build lab, will go through a CrossGen, get a CrossGen body of the code, that's AOT copy of code. And some of them may not, because we need to contain that size. At the startup time, we actually kick in quick JIT. And when we reach a steady state, we'll find right candidate to do for up. I think it's similar to HotSpot, but not as sophisticated yet. And we still have a long gap to close, but we are making that very big step for ourselves. Because at runtime, burn in that assumption, one IO mapped to one native, to remove that is actually a tremendous amount of work. Because that assumption probably leak out anywhere in the places that you did not expect. So the heuristic of tiering, how to determine hot method. I will call it method worthy the CPU time to be recompiled. We have a bunch of algorithms, we try to play with it, and since this is a space and we are relatively new, so we try kind of hit count, a standardized hit count. And because we try standardized hit count, at the end, we found out it did not make that much of a difference, so we picked 30. We know there are a bunch of other stuff that we could do. For example, we can use simple profiling to trigger for optimization at a different time, and it's possible we can use machine learning. We can choose dynamic feedback and try to figure out that. But it is kind of in our roadmap, but not delivered yet. And when to trigger queued reject work? High-level philosophy is avoid disturbing startup phase. Let's go back to our friend, my beautiful picture here. Remember we talked about startup phase behavior was a runtime initialize. You load type, you JIT, you run user code, you JIT, you run user code, you JIT, you load type, you run user code, you JIT. And thank God, I go to the user code, I continue execute on user code, life is happy, right? It's perfect. No, it does not. You will execute your user code for a while, and then you will realize that many different workloads will have this behavior again. You will start to JIT again, you will start to load type again, you will run teeny bit of user code, you JIT, you load type user code, and after a certain while, and then you see a stable state. Many things kind of fit into this kind of workload. Azure function, it's a function of service, but actually did not quite implement it as like Amazon's Lambda. It actually has a hosting process, application, and it's a hosting process. That, when that process is running, it is actually receiving queries that from the user, that receiving functions from users. So as it receives new functions, you are going to see that startup phase behavior. And we would like to give the startup phase behavior to not to do extra JIT work. The goal there is trying to JIT as fast and get to a stable user code, right? So this is how we do it. Call count has an overhead and background JITting, and also can slow down the startup. So what we did is actually, we kind of remember when is the last time that we need to do JIT a new method. If over 100 milliseconds and we did not encounter a JIT activity, we consider ourselves going to a steady state. Then we start triggering hit counts. When hit counts get to 30, then we just say, queue that method, and that method no longer do call counting anymore, because you want to remove that kind of activity and overhead. And this diagram, I hope is not an eye chart for you. Music store is a kind of .NET well-known benchmark, and one of my guys pulled this together. The brown spot that you are seeing over there on the top row, can you see it? Those are actually places that consider startup phase. That means you do encounter JIT within less than 100 milliseconds. The black spot between the brown the brown bar, I circle in red, but I did not circle all of them. Those are actually considered steady state. Those are the where that actually call counting happens and queue the work, and hopefully we'll be able to drain the work. And I went to my guy and asked, did we ever drain the queued work? He looked at me and said, yeah, after 25 seconds when Roslyn compiled Roslyn itself. I said, really, 25 seconds? He said, yes, 25 seconds. So it's going to be workload dependent. Depends on the behavior, right? If your workload do not have this kind of startup phase behavior, you will get to steady state earlier. And if you continue kind of in and out, that kind of startup phase, then you just will get to a steady state later. But if you have work, you will always queue it up. We'll find the right place to do the work. So we do the measurement again. When my guy showed me this picture, we look at it and we say, this cannot be true. This is too good to be true. JIT and CrossGen plus tier JIT is exactly the same. And then we went back and said, how can this be true? And our JIT dev said, of course it is true. You are measuring the same code. Because it really doesn't matter if it's the first time that we use JIT and follow-up JIT or CrossGen, but you are measuring steady state, tier JIT happened. So it is the same code. And this is just proof that we do reach that repair. So this is where that we see the philosophy about AOT and JIT can work together and try to complement each other, and rather than like head-to-head compete. And it has been always our design philosophy. Third generation of AOT, name is TBD. We are process of building it. Remember that same set of questions that we asked earlier? We are going to ask again. Where can the images be generated? We want to say arbitrary place, ported to arbitrary place. That means we want a true portability. We want to be able to have code generation and execution machine, have mismatched platform and mismatched architectures. This is actually really important because if you think about your build lab, if you are encountering a new architecture or a new platform, how fast can you get hold of that thing in your build lab? Actually, it might be a while. You will really be happy when an AOT tag actually allowed you to leverage your current machine configuration to generate arbitrary target. And that is actually really a powerful thing. And does it need to support servicing event? Yes, we do need to support servicing event, but we also have some observation. Being CLR, being that unfortunately saw that had to power arbitrary scenario, we observe some of the scenarios, servicing event may not always happen. In .NET Core, we enable people to do self-contained application. They can bundle everything and deploy it out. When they service, everything services together. Even in our Microsoft Cloud like Bing, when they take out .NET Core dependency, they no longer under the blessing of Windows Update. They actually know if they're going to service in a runtime or not. And if infrastructure is running, it's your closed system, you usually do not allow arbitrary servicing event to happen. So in that particular configuration, you should be able to optimize for non-servicing scenario, right? We talk about the gap between the NGEN and talking about the gap between the CrossGen. We scale back, but do we always have to scale back? Maybe not. So this is generation of AOT tag. We actually would like to give people that flexibility and to decide what's your deployment scenario, what's your servicing scenario, what works for you. Out of box will work good, but if it does not match your criteria or you want the last bit of mileage, then you go there. What size is susceptible? Size good is good, but we will also ask about, can we support the extreme size requirement? How small can we get it to, right? Not everybody care about get to as small as possible, but there will be some people care about it. And when you go to that as small as possible, does the developer need to intervene? Maybe yes. I think just like the Growl VM talk, they're talking about like pure AOT and then something just did not work. But this particular case, we believe JIT will be there. However, if you want to choose in between what you can take off on your image, then you might be having that choice. Trust signing is something that we will never give up, so that is good. Deployment, we actually did not talk about deployment. We kind of touched it once, but didn't come back to this. When you're thinking about deployment, download 200 files and download one file, it's actually a big difference. So in this particular AOT tag, we would like to get to a point that we can generate single file deployment. So I kind of want to do a recap in the future, and if I have time, I can talk about CoreRT a little bit. But if not, then that is actually okay. So I kind of put into 3 boxes, kind of point out the journey that we just walked through, NGEN, CrossGen, and AOT, right? NGEN is the one with the standalone native images. CrossGen and 3rd gen is actually not going to have extra file. In fact, the 3rd generation might generate less file. And NGEN always generate on the target machine. CrossGen actually could be generating different machine with similar flavor. And the third generation should be arbitrary one. And NGEN itself is fragile and need to repair. CrossGen is not fragile, does not need to repair. AOT, third generation AOT can generate fragile and can generate non-fragile. So we believe both scenarios actually are both important. And NGEN images are not copy deployable. CrossGen is already embedded to IO, so it's kind of copy deployable. And the third generation AOT is also copy deployable. NGEN was one, if you think about Java world, one jar file mapped to one jar DLL. CrossGen is embedded into that jar. Third generation of AOT should be able to support N-to-1 mapping. It could be one-to-one mapping. It also could be N input mapped into one. That eventually give you a single file deployment if you want to. A lot of the time, you may not want a single file. A lot of time, you may want 3 files, 4 files, and you're happy. But you would prefer not to have 200 files. And NGEN itself, I didn't mention that earlier on, it actually depends on the presence of the runtime. CrossGen itself is a standalone tool, so that tool itself, you can copy and use it. Third generation one will be also a standalone. Now I want to talk about the future of JIT. We would like to catch up more with Java world. We finally have tier compilation. We're actually pretty happy that we are able to use that to blend the AOT and JIT. We have some flavor similar to that, but we only use it in add and continue. Not until today that we kind of use it in the release configuration, right? We are missing on-stack replacement. That actually has its own challenge. For example, today, code method with hot loop cannot be rejected. So some of the style of the code, if you just write a main and loop inside, recursive, we can patch it, right? But then if you are looping inside, then we kind of got stuck. So we really would like to have the on-stack replacement. Today, our tiering heuristic will say, if you see a method with a loop, maybe don't try to do quick JIT in case we got stuck. So we do some compromise. On-stack replacements also will enable our JIT to do speculated devirtualization optimization. That later on, that is no longer true, we can go back and fall back to, let's say, CoreGen. We want more sophisticated reduced heuristic. Today, hit count 30. Is that really true? Do you want to weigh in the good CoreGen, bad CoreGen? Is it worth it to go to a good CoreGen immediately? Or do you even bother to do a quick CoreGen, right? So we are looking into that. And that also opened up to tier and JIT. When JIT can be in a place that does not constrain by the throughput of itself, and maybe we can pick up a different reverse CoreGen. I think I ran out of time already, right?
Pretty much.
Yeah. So I'll just quickly run through our experiment. This experiment is actually quite similar to Ground Native. It's a CoreRT. What we did is actually we do a pure AOT. We really take the JIT out. We rebuild our runtime to the minimum. And this is a stretch experiment. We want to know how fast can we go. And we actually go pretty fast. We actually, in our benchmark, we see we're about 50% faster than NGEN. And how small can we go? Our footprint, actually, an application that one of my guys tried, he quoted me 400 KB. That was actually really impressive. And that exe that we generated is actually the runtime got embedded to the exe, like, the GEC embedded in there, just pretty much like Cloud Native. And it's platform native. So why didn't we ship it yet? Well, just like Java, the same problem exists in our world too. Tree shaking with reflection is not very friendly. And our ecosystem over time, Java and C# both have existed for a long time. That dynamic in the ecosystem, like class library, dependency injections, and places using reflection that you cannot think of, all exist. And those things come into CoreRT, it just make it really hard, make it just work. Certainly, developer can go in, and we do have strategy on how developers should help in directing what to be code-generated. And we also concluded that a perfect whole program analysis is most likely not possible. We have interrupt, we have reflections. A whole program analysis, you assume a closed system. I don't have a closed system. So we can do a good job. Can we do a perfect job? No. But is a good job acceptable or not? Good job may be acceptable for some people. Actually, our being front end, because he's desperate for performance, good job is good enough for him. He actually deployed one of his servers with CoreRT, even though we told him we are not shipping it. He said, it's okay, I really want that last mile. So you're going to find your customer, all the different ones. One wants a servicing guarantee, quality guarantee. The other one says, I don't care, please give me as much as money on my gas, right? But we generate a bunch of ideas and actually feedback to the mainline product. Actually, the third generation of AOT is a large chunk of the work from CoreRT when we build a compiler, and we bring it back to CrossGen. Yeah. So I think that's kind of concluded my talk. Do you have questions for me?